Hi, I'm Katelyn Hertel,
And I'm Kelby Stockstill.
and we are the co-founders of the Unicode Unicorns.
So, Unicode Unicorns are a hackathon group that started last year in 2018 at the NASA Space Apps Challenge to invite different kinds of people, hackers, designers, scientists, to solve everyday problems using data available through NASA. And so, our goal for that project was to model sea ice in the Arctic Ocean.
And so we were successful. We were able to map the sea ice last year, but we knew there was so much more we could do. And during the hackathon last year, I came across Mediamatics and I requested an API key. And they came back to me and they said, hey, tell us a little bit more about your project. And we had some correspondence back and forth. And we started learning a little bit more about what Mediamatics does and the data that they can give us. And we realized that was the thing that was missing. We were missing weather data from our calculations. Sea ice has a lot of things that can contribute to growth or regression, and weather is probably the biggest contributor to that. And so when we found Mediamatics, we realized, wow, we just opened up a brand new window for us to go through and see what we can come up with. So we started researching more about Mediamatics. We started researching more about sea ice. We spent a full year basically just doing research. We spoke with a lot of scientists out there, especially at the Cryospheric Sciences Laboratory from NASA's Goddard Space Flight Institute, the NSIDC, and then, of course, people at Mediamatics. And through talking to these scientists and engaging them and asking them what they do all day, we realized that there are very important weather metrics to sea ice. And so we immediately knew that we had to include things such as wind, humidity, temperature, and radiation.
One of the other things that we also learned during that process, speaking to those scientists, was the different kinds of sea ice data that's published. There's two specific kinds, sea ice extent and sea ice area. Now, the NSIDC publishes sea ice extent because during the summer months, there's surface melt. And traditionally, the concentration of sea ice throughout the Arctic Ocean is measured based off of the passive microwave emissivity of the surface. And so if there's surface melt, like during the summer months, on top of the ice, it looks like water rather than actual ice. And so the sea ice concentrations are lower. They're measured lower than what's actually there. Because of this, the NSIDC only publishes sea ice extent, which is kind of like boxing those sea ice concentration values as either 0 or 1, rather than adding each one of them up. And so what the end result is this thing that looks like just a map of where ice is, not how much there is. But our goal was to measure, to predict how much ice, not just where it was.
And so we did some research and we did find that there is a satellite out there. It's called Terra. And it does look down at the Arctic Ocean. It looks at all the oceans. And instead of publishing the actual satellite images, it creates a 3D model of the sea ice. And when these are published to the naked, uneducated eye, it looks like there's just a landmass of sea ice in the Arctic Ocean as if it were Antarctica. And we know that that's not the truth. We know that there are ice flows in between different icebergs. We know that the ice is constantly moving and changing its shape. And therefore, that model that comes out from that satellite kind of gives us the wrong idea, right? It makes us think, hey, there's more ice than there actually is. But in reality, we know that there's much more open water in between those icebergs. And using this data and this project, we actually found out that our climate change statistics are a little bit off, and we're actually in a much worse situation than we thought we were. And so accurate calculations are very important to climate change. It's important to climate change predictions and how we're going to deal with this to try to save the world we live in.
So that brings us to this year's challenge, where we knew about this issue with how this data was reported. And one of the challenges at the 2019 Space Apps competition was to find this lost data and to correct for it. And so we knew immediately how to apply that kind of prompt. We knew immediately what we were going to try and correct for. We were going to try and correct the sea ice concentration values. Rather than just measuring what water was on top, we wanted to measure what ice was there. So we needed to correct for that surface melt. Given that prompt, we found one set of data published by the NSIDC that used high definition imagery to analyze how much ice was there, how much surface melt was there, and how much open ocean was in each of those images. And it's so selective. There's only so many places that they could draw these images from that we didn't know whether or not we could find from the NSIDC or from NASA applicable weather data. But we did know that we could draw that from Mediomatics simply by setting the parameters of their API request to the specific locations and dates that these images were taken.
Mediomatics was definitely integral to this project and also to just our research and fundamental understanding of how weather works. I mean, I've learned so much, and suddenly I have a very big passion for sea ice, which is something I never thought I'd care about. And Mediomatics definitely gave us the tools to do what we needed to do. And given that our data sets are so limited, it was also really hard to find weather data at first before we had Mediomatics because, these models go back years and years and years, and a lot of APIs out there are, their historical data is actually 24 hours instead of just live.
It could
And
have
so
so easily been that in this data set, there were specific temperatures, but that doesn't give us any kind of context about what's happening. We found through this project that aggregate data was the most effective at predicting whether or not there was surface melt, and that would have never worked if we didn't have a API call, a request, a data set for temperature over the course of the entire 3 years rather than just at the points when these images were taken.
So this year, on Friday, October 18th, we started hacking at 6 p.m. and we hacked the days and nights away until the following Sunday at 12 p.m. when we had to do our demo and sit for judges and answer questions. And in that time, we accomplished a lot, which is surprising because when we talked about this project, it just seemed impossible. Kelby and I are not developers. We each have our own day jobs. We like to code on the side, and all this research is just for fun. And we kind of had an impossible task in front of us. I mean, what is machine learning even? And so we had to learn a lot. And, I was taking a couple courses online, trying to figure this stuff out. Kelby has been studying, has a background in math, and is really good with calculations. And so together we set out on an impossible task and we actually succeeded. And Kelby's going to tell a little bit more about what we did during the hackathon.
So we had our data set and we had access to a lot of weather data. We could specify what kinds we wanted, when we wanted it, and perform manipulations on top of that. So given the short time frame of what we could accomplish within 48 hours, we set out to do some data analysis based off of just linear regressions and trying to predict based off of a combination of different kinds of weather metrics, whether or not we could predict how much of the water that was measured by those microwave emissivity measurements taken from satellites was actually open water versus just water sitting on top of ice. So we took our data set from the processed images and we called a few different metrics from Mediomatics. We called temperature, humidity, radiation, and wind. Initially, we started with just what the measurements were at the time, at the day that the photos were taken and processed. Based off of that, we tried a bunch of different kinds of combinations in order to predict what that actual true water amount was. So our project, for your ice only, aimed to predict the true amount of open ocean water in the Arctic Ocean. We had a limited data set of images and we had all the weather data that we could pull in using Mediomatics. So we were aiming to use weather data that was collected to predict how much actual open ocean water there was given the amount of water measured by the passive microwave emissivity. So we have all of the water and all of the weather data. We wanted to predict just what the open ocean water was. So initially, we cultivated a data set of weather data surrounding these different locations at the entirety of the 3 years between 1999 and the end of 2001, so that we can get some kind of idea of what the context of the surface melt was. And then from that data, we aim to create some regressions in order to predict what amount was open ocean water. The initial regressions that we had based off of just the immediate weather and just what was available of all water were initially pretty bad, some of them going below 0.1. It was a difficult process to get through as we were trying to figure it out.
But we were were really excited that we even had
Right.
under
We,
point
we,
zero
we'd
one.
gotten to the point where we could really look at it. We had gone through and like processed all of the data from the NSIDC, which takes forever because sometimes it's in ridiculous formats. Sometimes it's just in text. Sometimes you have to process it from just bytes. It's very difficult to get to that data. However, we had gotten through that, and now we could pull weather data from Meteomatics. And in comparison, it is night and day, going from
Yeah.
processing bin files to just using an API call to gain all of this weather data.
And so when we had under point zero one, we were pretty happy because at
We,
least
we
we
were
had
we were
something.
trying to predict something. We had something, and then from there we can start working more with the data. Well, it's not just what the temperature is at that time, but what temperature was over the past certain amount of time. Let's look at aggregated data. And so we had the entire 3 years of data, and we can start transforming that data into 7-day aggregates and 30-day aggregates to see which ones perform better. And then we had all of these different data points at that point: 7-day aggregates, 30-day aggregates, immediate weather data. And we could use a stepwise regression in order to go through each and every one of those metrics and identify which ones were most appropriate for predicting. And so given the 48-hour time constraints, it was so easy to just pull in more additional weather data and then run it through something that could easily try and figure out what works best. And what we ended up with was a model that used only the measurement of all water that was measured, what comes from what we could find from the NSIDC published in that ice concentration data, all of the water, plus the 7-day aggregate of temperature and the 30-day aggregate of humidity. And we could predict what amount was actual open water with an R-squared value of 0.892. It was awesome.
It
It
was so
was
great.
great.
48 hours, didn't know much about machine learning, and we have a model at 0.892. Honestly, we were blown away. But we just realized how important this weather data is, and Meteomatics makes it so easy to just pull it in. And because of that, our project is not just applicable to the Arctic Ocean and where we put it in the Beaufort Sea, but it's applicable to anywhere. You can just plug in your coordinates that you want to see. As long as there's ice and ocean, you can run our model on that area.
Right. It
And
wasn't
so
that it was just for the Arctic Ocean. It was
mhm.
given that we need to get weather data based off of exactly the data that we found. And there's almost nothing available. So it needed to be exactly for those points. We didn't have to worry about it. And so any other kind of study where they need exact locations and exact dates, they can easily gather those from Meteomatics, no matter where it is in the globe.
So, our project has a lot bigger applications than what we just did in 48 hours. Like we've been saying, it was only 48 hours. And if
Mhm.
we were able to accomplish this much in just 48 hours, imagine what this project is going to look like next year.
So as far as our next steps, initially we had a small sample of published images that were processed that we could use immediately. But that was from a larger set of images available through the US Geological Survey and the Global Fiducials Library. These images are slowly growing. They're becoming more and more available as they get processed and go through the bureaucratic process of getting published like this. But they're available now, and we could process these images in order to add to that sample. In addition to that, we can also look through Meteomatics' extensive API to find additional pieces of weather data, additional aggregates that we can use in the prediction. So by increasing our sample and increasing those independent variables that we're using to predict the true amount of open ocean water, we can hopefully improve our model.
The Unicode Unicorns team, especially Kelby and myself, would love to thank Meteomatics not only for its data and what it's able to give the general public, but for also assisting us personally and being there to answer our questions, especially Sam Nixon. All weekend I was on the phone with him where he was very excited for us. They've been super helpful, and we wouldn't have been able to do this project without Meteomatics and the weather data that made this happen. You can find us at Unicode Unicorns on Twitter. You'll see a little bit more of our process, how we went along. We documented our journey pretty well on there, but we're not done yet. There's a lot more work that can be done. And we're confident that with a regression model that's accurate and with pulling in more weather data, looking at more sample, we'll be able to successfully predict sea ice concentration at any given coordinate that you give us, giving us accurate predictions for climate change instead of what we have now, meaning that we'll better be able to understand what's happening to our world, why it's happening, and what we can do to stop it. Thanks for your time. I'm Katelyn Hertel.
And I'm Kelby Stockstill.
And we are the Unicode Unicorns, and our work is not done yet.
Stay tuned.